All right, so welcome back to the last section in Chapter 9. This is section 9.3, and we're still doing hypothesis testing. But now we're going to take a look at how to do hypothesis testing on two dependent samples. Also, sometimes referred to as matched pairs. Right? The key idea here, the key concept here, is that this section is going to take a look at hypothesis testing involving the mean of the differences of the values from two populations that are dependent in the sense that the data consists of matched pairs. Wow. For testing, whoop, I didn't want that. For testing hypotheses involving, and what is this involving? Involving the mean of the differences of the values from two populations that are dependent in the sense that the data consists of matched pairs. Okay, that's a lot of words. Basically, here's the idea. Most of these are going to fall under the before-after measurement. So matched up, we measure something about a data point before treatment. We apply treatment, we measure it after. Before and after, right? There also could be scenarios where the matched pair nature could be something like, is there a relationship? Do husbands and wives, do they tend to marry people with the same IQ? Do they tend to marry people with the same educational level? That sort of thing, where you could have matched pairs in different scenarios. But most of these tend to be the idea of the before and after, right? This kind of falls under the idea of good experimental design, right? Using dependent samples with matched pairs is generally better than using two independent samples to compare groups. This really gets back to the idea of the before and after, okay? Now, when we do a couple examples, we'll see. These are probably, of all the two dependent sample hypothesis testing, the hardest, right? So our objective is to use that hypothesis test, to use the differences from the two dependent samples to test a claim about the mean of the population. Okay, now I want to point out something. We're testing a single claim about the mean of one population. So why is this two if we're testing a claim about one population? Well, what happens in two dependent sampling is we take the two samples, we find the difference between every paired data, and we create a third sample from that we're going to call D, which is the individual differences between the two values in the matched pairs. Mu sub D is going to be the mean of that set of differences. D bar is going to be the mean for the sample. S sub D is going to be the standard deviation of the differences. And N here is going to represent the number of paired data. Okay. Our requirements are that our data sets must be dependent, that is matched pairs. By requirement, if they are matched pairs, the sample size here is only one thing. There's no data set 1 has 20 and data set 2 has 30, because if they're matched up, if there's 20 in the first, there's 20 in the second. Of course, simple random sample is always in here. And size requirements. That is, the number of pairs has to be large enough, or the pairs have to have a normal distribution. Okay. The math behind the scenes is this business. Okay. These are always going to be sample standard deviation problems, so they're always going to be at their core a t-test. Right? Okay, let's take a look at what's going on. Here is our first example. A shoe manufacturer claims that athletes can increase their vertical jump heights using the manufacturer's training shoes. The vertical jump heights of 8 randomly selected athletes are measured. After the athletes have used the training shoes for 8 months, their vertical heights are measured again. I'm going to highlight that because that's the key thing here, right? I've got a sample of 8 athletes, and I'm going to measure their vertical jump height. Then they're going to wear these shoes for 8 months, and we're going to measure them again. So I'm going to have the vertical for the before the shoes, the treatment, and I'm going to have the vertical for the after. And then I'm going to be able to compare those two data sets to say, hey, do these shoes work? Right? Now I've got a table of values here, and the vertical jump heights are measured and shown in the table. At a significance level 0.1, can we support the manufacturer's claim? And remember, the claim was up here, and it said that the athletes can increase their vertical jump heights. So I wear these shoes for 8 months, do whatever they tell me to do, train in them, my vertical should get bigger. Right? All right. I'm supposed to assume that the vertical jump heights are normally distributed, so that's good because my data set's small. I only have 8. Right? All right, so let's see what we got here. My table here says athletes are 1 through 8, so this is the number. Right? So we got the number of paired data sets is 8. So that tells me that n is 8, because in paired data, n represents the number of pairs that you have. Okay. Now here's where things get really difficult. My claim has to be about the mean of the differences, right? But before I can make a claim about the mean of the differences, I'm going to define what differences means here, right? So what does D, the difference, mean? Well, I'm going to say that D means new minus old, meaning the difference will be the new jump height minus the old jump height. So like for athlete number 1, D would be 2. And for athlete number 2, D would be 3. And athlete number 3, D would be 0. And how am I getting these? I'm taking their new jump height, subtracting their old jump height, and that's giving my D values. For athlete number 4, D would be 1. For athlete number 5, D would be -2. Okay, now there's a negative number. Does that make sense? Sure. If positive numbers means their jump height increased, negative numbers just means their jump height decreased. For athlete number 6, our D is 2. For athlete number 7, our D is 5. And for athlete number 8, our D is 3. So this new third data set that I just created here, by finding D values, that's the data set we're actually going to test. That's the data set that the claim is going to be against. Right? So here's where it gets tricky. If the claim is that the jump heights increased, and we define D as new jump height minus old jump height, then the claim of an increase would mean that the mean of the differences better be greater than 0. I'm just going to let that sit with you for a moment. The shoes make me jump higher. If the shoes make you jump higher, then D should be a positive number. Or the mean of the D's should be a positive number. As a pair of hypotheses, it's still going to be about a null and an alternate. Since our claim does not have equality in it, it'll be the alternate. The mu sub D is greater than 0. Then our null would just be that mu sub Z is 0. Remember, we're going to set it up. Our claim is the alternate. Our data, well, our data is literally that new set D. That data set of 2, 3, 0, 1, -2, 2, 5, 3. That's my data set. So basically what happens here is in a 2-sample dependent, we create a third data set D, and then since it is a single data set, we just run a good old-fashioned t-test on it. not a 2-sample t-test, a plain old t-test. So under stats tests, I'm running option 2 here. I'm running a t-test. Okay? But I don't have statistics, I have data. And when I have data, I first need to put the data in. So I'm going to go to my stat list editor, clear out that garbage, and I'm going to type this data set in. My data set is 2, 3, 0, 1, -2, 2, 5, 3. Now we'll go back to stat, over to test, run that t-test. I'm running a t-test on data. The equality statement from the null hypothesis is that it should be equal to 0. My data is in list 1, my frequency is 1. My alternate is that it's greater than 0, and I'll calculate. My test statistic, should I need it, is that 2.3, but what I really need is my p-value. I have a p-value of 0.026. When I compare p to my alpha of 0.1, I see that p is less than alpha. When p is less than alpha, we reject the null. But our claim was the alternate. When we reject the null and the claim is the alternate, we say there is enough evidence to support the claim of a higher jump. They can increase their vertical jump height. So what did I just find? Well, I did a 2-sample dependent hypothesis test. The math says take 2 samples, turn it into 1 sample, and then test that 1 sample. Now, I calculated set D here by hand because these numbers were super simple. I did not have to do it that way. Let me show you another way. If I wanted to, I could go back here and in set 1 or in list 1, I could put in the old jump heights. 28, 35, 32, 30, 32, 30, and 27. And then in list 2, I could put the new jump heights. 26, 25, 25, 29, 33, 34, 35, and 30. Then over here in list 3, I could have the calculator find D for me, find the differences. So the way that I do that is I'll scroll up until L3 is highlighted, and then down at the bottom of the screen, see where it says L3 equals? I need to type in new minus old. Right? Remember though, new meant list 2 and old meant list 1. So I'm going to say list 2 minus list 1, and boom to boom to boom. Do you see how it found the same values I found by hand? 2, 3, 0, 1, -2, 2, 5, and there should be a 3 down at the bottom, which is just off the screen. Perfect. Now I could run that test, that t-test, and say, whoops, test, t-test, and say use list 3. Those are the same values we got before. I'm just doing more of the work in the calculator. So why would I do that? I don't know. If D was hard to figure out, like if the numbers were ugly, it might be easier to let the calculator do the work. Or if it was a really, really big data set, it might be easier to let technology do the work. But in general, whether you calculate D by hand or let the let the calculator do that for you. It doesn't matter. It can be solved either way. Okay? All right. Let's try another one and just make sure. Okay? An instructor for an SAT prep course claims that the course will improve the test scores of students. Why else would you take it? Okay. The table shows the critical reading scores for 10 students for the first 2 times they took the SAT, before taking the prep course and after taking the prep course. Okay? At a significance level of 0.01, is there enough evidence to support the instructor's claim? Okay, so if the prep course works, these numbers should be bigger than these numbers. So if I define D to be the second time they took the test minus the first time they took the test, then claiming that the course works would mean that the mu sub D should be greater than 0. You'll find that in a lot of these dependent ones, 0 shows up. Okay. Hypotheses, a null and an alternate again. Since there is no equality in the claim, that's our alternate, that the mean of the differences is greater than 0. Our null would then be that the mean of the differences is equal to 0. Right? Our data needs to be at set D. So I'm just going to put down here, calculator, because I'm going to do the whole thing in my calculator. All right, so let's get started on that. Let's clear this, stat, edit. I need this, wait, yeah, I need this gone, clear that. I need this gone, clear that. I need this gone, clear that, right? And now I'm going to start putting data in. In L1, I've got 300, then I got 450, and then I got 350, and then I got 430, and then a 300, and then a 470, then a 420, and then a 370, then a 320, and then a 410. 400, 520, 400, 490, 340, 580, 450, whoops, 400, 390, and 450. Right? Now, if D is second minus first, and second is in list 2, and first is in list 1, then over here, I need to do list 2 minus list 1 again. So list 2 minus list 1. Right? So I get those values. Data's in the calculator. I'll run the test. The test is a t-test on a single data set. The equality is 0, L3, but this time I still want greater than, so I calculate. I get a test statistic of 6.8. That's crazy huge. More importantly, though, I get a p-value. Look at that p-value. It's 0.0234 and then a 4. The 39 rounds to 4. E negative 5 means times 10 to the negative 5th, so move it left 5 places, 4 leading zeros. There's my p-value. Look at that p-value compared to that. It's way smaller. When p is low, the null must go. So we are going to reject the null. But the claim was the alternate, so what can we say? We can say that there is enough evidence to support the claim that the prep course improves scores. And there we go. Okay. One thing that I want to point out, right? In both of these examples, I did the second one minus the first one, and that made the mu greater than 0, because I'm trying to make the logic follow. If I want to show that the second score is better than the first score, then I'm going to take the second score minus the first score and show that it is a positive value, right? If I wanted, or if I had data and the logic, the claim was that things went down, then I'd want to take the first one minus the second one and show that that was positive. Right? So the logic of this needs to follow. How you set up your set D matches with the claim and then sets the hypotheses and runs the entire experiment. Okay? Please, if you have any questions, reach out. This brings us to the end of Chapter 9. Have a great day.